Welcome. In this video, we're going to introduce the first derivative test. We've already informally have been using the first derivative test. We've just been using it without a name. So let me give you a more formal definition, and then we're going to relate it to what we've already been doing. Suppose f is a continuous function over an interval I containing a critical point c. If f is differentiable over that interval, except possibly at c, then f satisfies one of the following descriptions. If the derivative changes sign from positive when x is less than c to negative when x is greater than c, then x is, and I'm not going to fill in this blank quite yet. If the derivative changes from negative to positive, then f is, and again, I'm not going to say what exactly is happening. And then there's a case where f prime has the same sign whether x is less than c or x is greater than c. So before I give it away and say what is going on, let's make a sketch. So here's a number line, and there's c. So on this side, x is less than c, and on this side, x is greater than c. So let's look at this first case. So we're changing from positive, so our derivative is positive here, and then to negative. What does that look like? Our graph is doing this. If you said this looks like a maximum, you are correct. So if the derivative changes from positive to negative, then f evaluated at c is a local maximum. Now let's explore the second case, and I'm going to use blue for this. So our derivative changes from negative to positive. So our derivative is going downhill, then uphill. What is that going to look like? Something like this. And if you said this is a minimum, you are correct. So when the derivative changes from negative to positive, then f evaluated at c is a local minimum. Now what about this final case? If we have the same sign on either side, so they are both, say, positive or both negative. What does that tell us? That tells us that f of c is neither a max nor a minimum. Example 3, using the first derivative test. Use the first derivative test to find the location of all local extrema for f of x equals 5x to the 1/3 power minus x to the 5/3 power. Let's start by finding our derivative. So here is f prime. We have 5 times 1 minus x to the 4/3 power divided by 3x to the 2/3 power. Next, we want to know when is the first derivative equal to 0. Well, this occurs when just this part of the numerator is equal to 0. So let's figure that out. Now that this part of the numerator is fully factored, it's easy to see that the first derivative is equal to 0 when x equals positive 1 and when x equals negative 1. Do we have any other critical values? Why, yes, we do. F is undefined, our first derivative is undefined here at x equals 0, since that would give us a 0 in the denominator. All right, since f prime is undefined when x equals 0, this is another critical value. Next, let's test some points. So again, I'm sketching a number line, and that divides the real number line into 1, 2, 3, 4 regions, and I used my critical values as my dividers. And the points we're going to test are x equals 2, x equals, negative 2, x equals 2, x equals negative 1/2, and x equals 1/2. The first derivative of f evaluated at -2 is less than 0. The first derivative of f evaluated at -1/2 is greater than 0. The first derivative of f evaluated at +1/2 is greater than 0. Finally, the first derivative of f evaluated at 2 is less than 0. That tells us that we have a min here, we have a max here, and right at x equals 0, we don't have a minimum nor a maximum. So when x equals -1, f is equal to -4, and when when x equals 1, f is equal to +4. So my minimum is at -1, -4, and our local max is at +1, 4. Finally, let's verify our result using technology. All right, you can see here I've graphed our function using Geogebra, and we can use this extremum to find that our local minimum and our local maxima are indeed at -1 and 1 respectively. And as we can see right here at 0, so let's kind of move around at x equals 0. If you notice, it looks like the tangent line is vertical there. So if we get really close, that looks like just a blue vertical line. All right, so we have used technology to verify that this point here, A, and this point here, B, on my graph, are indeed the only local minimum and local maximum. And here the tangent line is vertical, so that is neither a local minimum nor a local maximum, but we saw that here because the first derivative went from positive to positive. It did not change.